Okay, another calculus problem. So what we want to do is we want to find this integral. It's a ds integral, so it's a surface integral, right? And specifically, we see that we're integrating over this surface S, and S is part of this plane, and then it lies inside the cylinder. So a lot of useful information. Okay, now if I draw this real quick, I'll try to draw it nicely for you guys. This is our cylinder, and then we see that our plane, and I'll draw the axes real quick for us too. We'll let this be Z, X, and Y. We're not going to let it, it kind of has to be, that's what this cylinder states. But then you can see that this plane says something kind of specific regarding it. And it's indicating some sort of cut like this, right? So you could imagine this looking like a piece of chalk if you were to hold it across the chalkboard, or some lipstick if you were to, I don't know, wipe it across your whole face 500 times. It would look kind of slanted. Well, this is what our shape looks like. But what we want to do is we want to see this guy, right? We want this integrand to look a little bit differently, and we want to know what ds is. Well, ds is, it's equal to the same thing as n dA. And then if you ask me what n is, then I could tell you that n is, it's usually this vector we write as ru rv equal to n, right? And then we take the norm of n, and then we get, the norm of this, right? But since for us we see that we have a surface with a z, where z is the function of x and y, we can write it as this: zx squared plus zy squared, and then dA. And this is just, it's the same thing, it's just a little bit of a shortcut if you have a function z, if you have z as a function of x and y. And it's really nice. And then you can see that it has to lie within the cylinder, so then you put our integrating bounds over the cylinder. Okay. So the cylinder is going to be our bounds and everything like that. That's how this integral will work. Okay, so if you write your integral, now real quick, before I write the integral, let me just write out the integrand. So x squared z plus y squared z. Okay, what does this mean? It means that, well, we're going to use this as a substitution for z. So it's going to become x squared 4 plus x plus y, and then plus y squared times 4 plus x plus y. Now the reason why I'm doing this is because, as you can see this right here, if we use this to find zx and zy, then this will be a pure function of x and y. And we only have two integrals, so we have to have an integrand that is only of two variables. Right? Now that should make sense. That should be the reason why you want to do this, because you want to reduce the number of variables. Okay. And then I'm going to add a 1 here. And then, okay, then let's take zx here. So if we take the derivative of this with respect to x, this will go away. So it's just going to be 4 plus y. And then if we take zy, well, what's it called? Sorry, 1 second. This derivative right here is wrong. I should be punished for that. I'll write out, I'm not going to do it in my head. I usually do it in my head. But we'll do zx out loud here. It's going to be 4 plus, it's not even going to be 4. My bad. Oh no. Can't believe I'm doing Calc 1 stuff wrong here. It's going to be 1. If we do zy, it's equal to 1. That was kind of embarrassing. I just forgot how to do the world's easiest derivative. But it doesn't matter. So we have 1 plus 1, and 1 squared is 1, so that's why I didn't bother squaring these, because it's going to be the same thing. And this is equal to square root 3. Okay. So now we can rewrite our integrand. It's going to be this double integral over some region D. So I can change the region, because I'm changing from ds to nda, or square root 3 dA. And it's going to be x squared, 4 plus x plus y, and plus y squared, 4 plus x plus y. And then I'm going to put the square root 3 actually in front, because it's just a constant. But this formula would tell you that would be in the back here, next to dA. And this will be dy dx. Actually, instead of calling it dy dx, let me just call it dA for now. Okay, now I want to find the region D. And we can see that the region D is bounded by this, right? because it lies within inside the cylinder. So whatever it is, like the plane can go, like the plane goes on for infinity, right? But it has to be within the cylinder. So the cylinder is our limit here. And here's our cylinder, radius 2. Right, and then we can see that we can describe the cylinder using theta and using r. So then its range, or its radius, is from 0 to 2. And then theta is from 0 to 2 pi. Okay, and this next part. Okay, so what you want to do is you have x and y equal to r cosine theta and r sine theta. Okay, it's important you put r instead of 2. Very important. Don't put a 2 for this r in here. Okay. Okay, now what we're going to do is swap all the stuff in here. But I'm not going to swap it in real quick. I'm going to actually rewrite this integrand using it and then swap it in. Just because I don't want to keep rewriting the integral signs over and over again. There's a trick I recommend you do. So if I put an x squared here, it's going to be r squared cosine squared theta. And then this will be 4 plus r cosine theta plus what? R sine theta. And then the y squared here, you can see that it's going to become r squared sine theta, sine squared theta. And then same thing goes, it's a 4 plus r, r cosine theta plus r sine theta. And as you guys can imagine, what we can do is we can factor out this 4 plus r cosine theta and this 4 plus r cosine theta plus r sine theta. These are the same term. And then we're left with just the r squared cosine squared r squared cosine squared theta and r squared sine squared theta. And as you can see, cosine squared plus sine squared is just 1. So then we're left with what? Just r squared 4 plus r cosine theta plus r sine theta. Okay, so this is our new integrand. Comes out really nice. Okay, now I'm going to go back into green here. Okay, so we know that our new integral looks like this: square root 3 from 2 pi to 0, and from 2 to 0. And it's going to be r squared. And real quick, what I'll do actually to save some time is I'll use the feature. Oh, damn it, did not want to do that. I'll just drag this guy over here. Like that. And remember, since I changed from x and y into r and theta, I have to have my Jacobian r. And now it's a dr d theta integral. And as you guys can imagine, what I can do here is I can do one integral at a time. So let me erase that. I'm going to do the first iteration in blue. So it's going to be 2 to 0. And there's r and r squared here. And there's r's in here. So I'm going to write this as r cubed times 4. Let me write that a little bit nicer too. 4r cubed. See, there's r and r squared here. And then this is going to become r squared times r, so r cubed times r. So r4 cosine theta plus r to the 4th sine theta dr. And if I integrate correctly, it's going to become what? Well, this would be raised to the 4th divided by 4, so it's just going to be r4 plus r to the 5th cosine theta, and then plus r to the 5th sine theta from 2 to 0. Now what I'm going to do is I'm going to insert the 2 into there, but before I do that, I want to do some factoring to make my life a little bit easier. So if I factor out the r5s here, so I get r to the 4th plus r to the 5th over 5, and I got cosine theta plus sine theta, and from 2 to 0. Okay, that way I only have to do it once. And yes, I'll make more space in a second. Now 2 to the power 4 is 16. And 2 to the power 5 is 32. So we get 32 over 5. And then this is cosine theta. plus sine theta. And then this will be the next integrand for this integral over here, but I'll make more space. Okay, so I'm going to do this next integral. And this will be our final integral, so it's going to be square root 3, 2 pi to 0, and this thing right here. So 16 plus 32 over 5 cosine theta plus sine theta d theta. And you guys can imagine that this will become square root 3, and this will be 32 pi plus 32 over 5, and then cosine, the integration of cosine is sine theta, and then the integration of sine theta is negative cosine theta. And this is being integrated from 2 pi to 0. 1 second. I kind of skipped a step on you guys. I should have not done that. It's correct. Don't worry. I didn't want to skip a step on you guys. This will be 16 theta. Okay. And now we're going to insert 2 pi and 0 into both of these. Now, real quick, I just want to show you guys a trick here. So this is... Okay, so I'll draw a sine graph here. And then I'll draw a cosine graph here. Yeah, I'll draw a cosine and a sine graph. They're the opposites of each other. Now, you should notice that this will be 2 pi right here. This will be 2 pi right here. That the area over here and the area over here are symmetrical. So, when you integrate sine theta and cosine theta from 2 pi to 0, that's 0. So, in both cases, we'll see that this will be 0. So, if I go here, now all I have to do is square root 3 times 16 theta, 2 pi to 0. And this will be what? This will become 32 pi square root 3. So right there is just a simple trick just to show you guys that, maybe using some calculus will help out, right?